Okay, so a little bit about me. I'm a former computer science educator. I'm currently a quote-unquote professional programmer. Honestly. I got interested in garbage collection because I used Ruby professionally for a long time, and that's, yeah, it's kind of a joke, but also and yeah, also I want to say, like, to what our friend the CTO said, if you're not interested in computers, then, you know, this isn't the right place for you, but I am, and I hope most of you are. It seems like you are, so that's really cool. So yeah, I use Ruby professionally. I had a lot of problems with that. I started studying it, and then I wanted to give a talk where I taught a conference worth of people as much as I could about what garbage collection is, how it works, what they can do to learn more about it, and the idea was that people who use Ruby in particular should understand how garbage collection works in order to write better Ruby code, write faster Ruby code, or understand the reasons why their code was behaving the way that it was, performance-wise, particularly. So I got really into it, and this paper, out of all the papers that I read in studying the subject, a few dozen, is my favorite. And yeah, this meetup is basically my dream come true, because not only because I'm speaking and I love to hear myself speak, but because it's such a fucking awesome idea, you know. And I wish that something like this was around 10 years ago, open to the public, because then, you know, I would be 10 years more advanced than I am now, which is not very advanced. So yeah, I think that's enough about me. The paper is a unified theory of garbage collection. It was published by Bacon, Chan, and Rajan in 2004. These are three guys that work at MIT, and IBM, excuse me, and it's a fantastic paper. So I'm going to give you a little bit of an outline of what the rest of this talk is going to look like. I'm going to speak for about 30 minutes total, hopefully, maybe a little bit more, maybe a little bit less, and then I hope that we can have some discussion. It seems like a bunch of you have read this paper, and hopefully you have some questions or some things to say about it, and we can chat about it. You know, being invited to be the first speaker at a meetup like this is interesting. We're kind of still playing it by ear in terms of what this thing should look like, but hopefully we can, you know, I know that there's some opinionated people in the audience. Don't act surprised, you know. So yeah, so I'm going to give a little bit of background about garbage collection as a subject area. I'm going to highlight what I think are this paper's contributions to the field. I'm going to talk about what my favorite parts of the paper are, and then I hope that we can talk about all of that at the end, or some of it. So as a show of hands, who has studied garbage collection like in any capacity before? Reading this paper included. Okay, way up, let's raise your hands. Okay, good. Nice, okay, that's a good number. All right, so how many of you have read the paper again? Okay, good, pretty good. Read the paper. You gotta read it a few times before you read it. All right, first you have to read it, and then you're like, do I want to read it? And then you read it. And then you're like, did I read it or did I read it? Okay? That's you know, I think that's another thing that I'd like everyone in here to take away from this meetup is that, you know, papers like this that are published by the, you know, prominent computer scientists that are doctorates and work at big companies. These people do research for a living, right? So you're not going to understand all of it, right? But the beauty of a lot of papers, and this paper in particular, is that you'll understand some of it, right? And you'll understand some, and then a little more, and then a little more, and you'll get the basic idea. And that's really cool. Like, read the abstract, read the conclusion, look at the sections, read the bibliography. If any of those papers sound interesting to you, do the same thing over and over again. Recursively walk that bibliography, and that's how that's how I learn anyway. Yeah, I don't normally recommend that people do things the way that I do, but I think that's pretty good. So, how many of you have hacked on a garbage collector in any capacity before? A few? Okay, I think actually that more of you have than you know. Like probably some of you have hacked on a garbage collection like algorithm before, and you haven't You might not know that, and that's another lesson that this paper has for you, for us. And how many of you are just here for the beer and pizza? And or me, because I'm so like handsome and charming. No other adjectives? Fine. Okay, cool. So first let's start with garbage collection. This is John McCarthy. It's one of the greatest photographs of all time. Here he is in the early 60s or so, playing chess against a computer. He wrote the program that the computer is running to play chess. And I mean, let's all just look at this picture for a minute. Is that enough? Okay, just look at the expression. I want to look at a computer that way one day, you know? Normally, I typically have a more scornful look on my face, but and if anyone here knows chat, I mean, it looks like it's kind of early on in the match. I don't know who won, but anyway, it's cool. There's robots in the background. Okay. So he's on this slide because he's one of the inventors of garbage collection as a concept, right? I have a joke where I say that 1960 was a great year for garbage collectors. That's because that's the year that both of them were invented, right? And that's an interesting idea that is sort of borne out in this paper and refuted a little bit in this paper. But the two major algorithms that we'll be discussing were both invented in papers in the same year, sort of inauspiciously. Neither of them are titled like, "Yo, I invented garbage collection," right? They're this whole other thing, but these algorithms fell out of that. So. And plus, like I said, some really good pictures. So let's talk about garbage collection as a background. In order to do that, this is the list of terminology that I think is important to understand. So garbage collection is on this list. That's kind of silly, but we have to know what it is, right? In order to give a good definition of garbage collection, I think we need to have pretty good definitions for all the other terms that are on this list, okay? So, what's a heap? Who wants to help me out? Anyone else? Anyone have a good definition for what a heap is?
A sort of tree structure?
It's a data structure that you have access to that you can allocate from and deallocate to. It's a big pool of blobs that you do stuff with, right? I mean, it's a tree structure, as Brendan says. Okay? Does anyone have no idea what a heap is and is really confused when I talk about heaps? No? So most of you are okay with that subject? Okay, so it's like a big pool of memory that you have access to in this paper, and for the purposes of this discussion, we're going to assume that this heap of memory that you have access to, you only allocate and deallocate fixed-sized chunks from this heap, right? It's a big bag full of marbles. When you need a marble, you take a marble out, right? When you're out of marbles, you're in trouble, right? And when you're done with the marble, you put it back in the bag. Okay, you have a bag of marbles. That's basically how computers work, okay? What about a mutator? Okay, so a mutator is specific to garbage collection terminology. I would say that a mutator is the part of your program that does the stuff, right? The mutator is the thing that takes marbles out and puts marbles back, polishes some marbles, annotates them in some way, okay? So if you have a big pool of memory and you want to say, this chunk of memory is an integer, it's the integer 1. This bit of memory is the value true. This bit of memory is, the head of a list, and then it points to the tail of the list, and that list contains a function structure, all of that stuff. Whoever's doing that work in your program is the mutator of the program. It's kind of abstract. That's one of the beauties of this paper, right? Because what it does is it takes something that's typically considered quite concrete and makes it into an abstract system, and I hope to demonstrate that more. Okay? Any questions? Yes?
Would it be reasonable to say that the mutator is mutating the heap?
The mutator is mutating the heap. Yes, okay. That's for sure true. Anyone else?
So is the collector.
Well, right. Right. Okay, so is the collector. So let's talk about the collector. Okay? So, and in some cases, like we'll see, the line between the mutator and the collector is kind of blurry, right? Who's mutating, who's collecting, whatever. Like I said, it's a computer, kind of all bets are off. But, so the collector is the part of the program that is specific to bookkeeping the memory in that heap, right? So that's, the collector has to know what's going on with all your available memory, what you can do, what has been done. It typically keeps track of things for you, right? And as you'll see, we'll drill a little bit more deeply into that. Okay, so that's heap, mutator, and collector. Any questions about that? If you don't really understand those on a basic level, then the rest of the talk might be a little bit challenging for you. So since this is a discussion, anyone, any questions? No? Anyone uncomfortable? You can like wink. You don't have to think of someone. I like being winked at anyway. So. All right, let's keep going. Yeah?
Did you skip garbage collection on purpose?
I did skip garbage collection on purpose because you're going to have to know the ones below it, and I give a nice definition of garbage collection on the next slide, and I remember that because it's right in front of me. So roots are interesting, right? Roots are sort of specific to specific implementations of garbage collection, but what I call roots are areas of your heap that can be reached without asking other areas of the heap how to reach them, right? So roots are something that are sort of inherent to heaps. They are your entry points into those heaps. In dynamic languages, in dynamic object-oriented languages, there's a really good thing to point to for the heap, or for roots, and like an example in Ruby, for example, of what a root object is in the heap is like the definition of the object class is a root in the Ruby heap, right? Because you have to be able to get to object in order to be able to find everything else in that heap. It's a very Ruby-specific example. Does anyone else have any contribution? Program stack, right. So that's another thing that would typically be in the roots, right? You don't have to ask, when the program loads, where the program starts, right, and how to access the data that comprises the actual program will typically be reachable from the roots as well. All right? And then barriers are a little bit more complicated, and we're going to talk about them a little bit more in detail. But barriers are types. A barrier is a mechanism by which the mutator it is through barriers that your mutator can inform the collector of certain things that are happening inside your program. And that's a little bit vague. I'm okay with that, okay? Barriers are important, yes?
I have a question about, I'm still like very new to this topic.
Great.
But, I was wondering, is there a reason why heap is the data structure in a garbage collector and not like another data structure?
All right, so I know the answer to that.
Okay.
Heap is a misnomer, and it's historical. So I joked saying it was a tree structure, because a heap is a sorted tree, but it's also the first implementation that was used for like malloc and free implementations. And so malloc free sort of style systems came before garbage collectors, and over time, the bag of dynamically allocated and free memory was traditionally called the heap because it was a heap. And it has not been true in 60, 70 years.
So the question was, why is it a heap? And the answer is, it's not a heap. Okay? It's going to make it a lot clearer. No, that's true. I mean, these things were invented in 1960, and things are different then. And now you just use the word heap, right? It's just that thing. It's there. It's great. Without it, we would be in trouble. So I'm going to talk a little bit more about barriers. They don't really need to be on this list because actually the definition I'm going to show you doesn't have the word barrier in it, but I want you to look at that word. Okay. So there you go. All right, so now here's my garbage collection definition for, this is like there's another definition that has none of that other terminology in it, but I just wanted to show you the terminology and to show you this stuff. So garbage collection is automatic memory management. While the mutator runs, it routinely allocates memory from the heap. If more memory than available is needed, the collector reclaims unused memory and returns it to the heap. That's general. That's kind of implementation specific in certain ways, but I'm happy with this, okay? So, any questions about this? This is garbage collection. This is a pretty good definition of garbage collection. If you've never heard a definition of garbage collection before, I'd throw this on the table, right? The garbage collection was initially invented because people that were writing programs thought, hey, wouldn't it be cool if we could write a program that used more memory than was physically available on the machine that it was using, right? So that's kind of hilarious to think about, right? But if you only have 10 marbles, right, and you want to pull 10 of them out at a time, You have to be kind of tricky to like, you got to keep 9 in the air. You might be juggling them or something. I don't know. That was a terrible mixed metaphor, but does anyone not like this definition or want to argue with me about it? Or tell me how great it is. Yeah. Okay, let's look at it. I think this is pretty good. Garbage collection is automatic memory management. That's why we're all here. That's why it's important. While the mutator runs, it routinely allocates memory from the heap. If more memory than available is needed, the collector reclaims unused memory and returns it to the heap. Unused maybe isn't the greatest word. Unimportant memory or something like that. So there are two big algorithms that were invented for garbage collection in the 60s, in the early 60s. And here's a comparison from them. This is the first time we're dipping into the paper a little bit here. And this table that the authors offer is really, it's one of the first things that, so this is my copy of this paper. And we've been friends for a long time. It's heavily highlighted and annotated, and I have stars next to things and everything. And I really like this table. It's on the second page, and the first time that I saw it, it was striking to me because I was like, wow, okay. First of all, these are two algorithms that are typically considered very different from each other, right? When you're writing in a garbage collector, you're not like, I'm either going to use that one or this one, right? No big deal. No, like they were considered very different and for very different purposes. So just the idea that there were the same number of rows for each, like alone, I was like, okay, like there was a lot of thought put into this table in particular, and the idea in general that these algorithms have a lot in common. So let's look at them. The two kinds of algorithms are called mark and sweep typically, but the authors call them tracing algorithms. And on the other side, there are reference counting algorithms. So let's go down this table and we can talk about each of the rows in this table. Okay, so we have tracing and reference counting. The collection style, okay? In what style is memory reclaimed and used, again, by the system that is doing the GC. So in tracing, it's a batch style, and in reference counting, it's incremental. So incremental means that each time something happens, there is a little bit of that happening, and batch means that you buffer things up and wait for a certain limit to be reached, typically, and then do it all at once. So it's the difference between a little bit, 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 and nothing, 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 a lot, nothing, 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 a lot. Okay? So cost per mutation. Okay? So every time the mutator does something, does the garbage collector have any overhead for that particular operation? In tracing, there is classically none. Okay? And in tracing and mark and sweep, you mutate to your heart's content, and that's it, and you'll find out what happens afterwards next, right? In reference counting, the cost per mutation is high, so every time you mutate, you pay that cost of reference counting typically, and this table is in the naive implementations of these algorithms, which are the initial implementations of them. That's the starting point, and that's the point that really informed people's opinions about the applications and performance profiles of these algorithms. So throughput and tracing is high, and in reference counting is low. Pause times in tracing are long. So Ruby, which is has a mark and sweep garbage collector, for example, one of the problems that I was initially chasing down was these long pause times. They suck, okay? They're in the JVM2, they're all over the place, pause times are bad, and we'll talk a little bit more about that soon. Pause times are long in tracing, short in reference counting, so there's a high long for throughput and pause times and low short, right? There's a relationship between those columns, between those rows. So real time, this is a bit of a confusing bit of terminology. Real time, no for tracing, and yes for reference counting. So all real time doesn't mean, real time has a lot of different meanings, okay? In this particular context, what it means is that in reference counted garbage collection algorithms, you are capable of conforming to a particular SLA as to the amount of time that you will take to do work that the garbage collection algorithm will take to do work. And in tracing algorithms, there's a sort of non-determinism that is inherent to that particular kind of implementation. That's a little bit much. You don't really have to know about the real-time stuff now. If you are interested in real-time garbage collection, I have a pretty good explanation of the issues involved in that on my blog that you can check out. And if you want to ask me any questions about real-time or you want to discuss it at the end, we can. But tracing, typically, no. And reference counting, typically, yes, in the naive implementation. And tracing can collect cycles, and reference counting classically cannot. Cycles are items in the heap which either refer to themselves directly or refer to something that refers back to themselves. So we're going to talk a little bit more about what that means right now. Okay, so let's talk about it.
Sorry,
Yes.
I'm a little mystified
Yeah.
by throughput.
Okay.
What does that mean in this context?
So throughput means that's a good question. Throughput would mean the amount of memory that you could allocate, and well, it's sort of meant to be a performance characterization of how much overhead you pay. So your mutator will have a high throughput when it doesn't have to pay a cost per mutation, and your reference counting will have a lower throughput because it does pay that cost per mutation. So it can do more allocations in a more predictable amount of time. So reference counting will do less more predictably, and mark and sweep will do more less predictably. Does that work for you? Okay, it's a little bit tricky, right? I would say if you were thinking about it, it would be the amount of stuff you can allocate and deallocate and how quickly you can do that. And throughput might actually be more a characterization of the mutator than the collector in this particular case. We could talk more about performance stuff too. Okay, so let's start with reference counting. So reference counting is basically the idea that when you're running a program, each time you want to access some area of memory in a heap, you will keep track of the references to that particular area of memory. So every time you make a change, you're doing that bookkeeping as you make those changes. So it's reference counting. It counts the references to areas in memory in your heap. Okay? And let's talk about this is a quote from the paper about the naive implementation of reference counting, and it says, the incremental nature of reference counting is generally considered to be its fundamental advantage. However, the cost of updating reference counts every time a new pointer is loaded into a register is typically much too high, much too high for high performance applications. Okay? So this kind of tries to tell you what the pros and cons of this particular kind of algorithm is. So the good thing about it is that it's incremental, right? Every time you do a little bit of work, you know that your memory is at the best state in its bookkeeping that it could possibly be, right? So at the end of each mutation, when the reference counts are done and the memory is allocated and deallocated, there's no extra work to do. So that's what makes it suitable for real-time applications specifically, right? You can say, I know that this algorithm will never pause for more than n microseconds or milliseconds or wherever you're at, because you know that that bookkeeping will be done, and you have a few more knobs to turn in that regard, right? And so that's cool, right? So let's look at that, and then let's look at what's really great that these authors have to say about it is that as a result of that issue, right, some form of deferred reference counting is typically used. So the result is delayed collection, floating garbage, and longer pauses, which are the typical characteristics of tracing collectors, right? So what the authors are showing you is that reference counting is awesome, except for when it isn't, right? And that the changes that are typically made to reference counting garbage collectors in order to optimize them make them look more like tracing collectors. That's pretty interesting, yes?
Are there any well-known examples of systems using reference counting?
Yeah.
Python.
Python. CPython uses reference counting.
I've heard of it.
iOS, yeah. So there are some languages that, in reality, no, right? We're going to hear about that. Like nothing really uses pure reference counting, And that's kind of one of the cool parts about this paper. So these are sort of surfacey definitions of these algorithms because I want to get to the heart. What's most interesting about this paper in a lot of ways isn't about garbage collection, right? There's higher planes at play here. There's more interesting stuff going on. So that's why it's okay just to talk this much about reference counting and market sweep, because there's a lot of literature about what those things are and what they look like in the real world. So let's talk about market sweep for a second. So market sweep is the idea that as you are accessing your heap, right, you will mutate and allocate and allocate and allocate until you can no longer allocate anymore, and then some other part of your program, some other thread, or some other unit of execution in your program will do that bookkeeping all at once. So as opposed to the incremental nature of reference counting, where every time an operation is executed, you pay that cost, in a tracing or market sweep algorithm, you allocate, 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 and then stop everything to do the deallocation where it's necessary so that you can then continue. Okay? So its fundamental advantages are the lack of permutation overhead and the natural collection of cyclic garbage. However, a fundamental disadvantage of tracing is that freeing of dead objects is delayed, resulting in long pause time. So, and this was the issue that I was experiencing with MRI Ruby. And how do you optimize this kind of algorithm? Well, it's funny you should ask, because one of the first optimizations that is typically applied is generational collection, which, generational collection is 1990s technology that is finally making its way to Ruby in 2014, which is actually good, and it's making it a lot faster, which is cool. So generational collection, this reduces the average pause time, but also introduces permutation overhead. Thus, it takes on both some of the positive and negative aspects of reference counting collection. Okay? So in order to make market sweep algorithms faster, you typically do something called create a generational garbage collector, where you have one area of your heap that's allocated from more often and another area of your heap that is allocated from less often, or maybe you divide up your heap by the size of the objects. But in any event, you need to use a barrier, going back to that word, in order to optimize a generational market sweep garbage collector into a generational collector. And once you have a right barrier, you have permutation overhead. And permutation overhead and right barriers are fundamental characteristics of reference counted garbage collection algorithms. Okay? So that's crazy, right? It's really interesting because it's this idea. I'm going to get more into that soon because I'm taking a lot more time than I want to. So this paper structure. So let's talk about these are the number sections of this paper that I have just copied. So it has a qualitative comparison that we've just gone through, right? A similar kind of treatment of these two very different algorithms. The authors then introduce this idea of algorithmic duals, right? Where they say that garbage collection in the forms of reference counting and market sweep are typically considered very different from each other, but in fact they are what the authors, and I believe this is a novel term that they coined in this paper in specific, and I have not found many other references to the idea of an algorithmic dual elsewhere, although I'm going to ask you guys questions about that at the end. They're like, okay, actually, they're kind of the same thing, right? Especially in their real-world implementations. Then they talk about hybrid collectors and show us that almost all production garbage collection algorithms are hybrids of tracing and reference counting. And that's kind of what those optimization slide quotes that I showed you show, right? They say that, okay, reference counting works until the performance isn't good enough, and then you make them look more like tracing algorithms. And then tracing algorithms are great, but then the pause times get too long, and you want generational garbage collection, so then you end up introducing barriers, which make them look more like reference counting. So then they go through cycle collection, which we talked a little bit about. They talk about multi-heap collectors, and then they discuss the cost analysis and space-time trade-offs of these different algorithms. And the cost analysis is probably one of the most applicable and beneficial components of the entire paper, where they actually create a fixed point formulation, which is like a math thing, I guess. And so basically, they take these two algorithms that were considered like diametric opposites of each other, and they create a mathematical framework through which you can measure the space-time costs of any garbage collection algorithm. Okay, which is incredible. And like, I cannot do it justice. You're going to have to read it like a bunch, and then you're going to read it, right? I finally am pretty confident with that material, and it took a really long time. Yeah, and I'm not very intelligent, so any of you will probably have a lot better time with me than that. Okay, so then they talk about the space-time trade-offs, and that's really interesting too. So I feel like this paper's main contributions are that it creates this formal framework for considering any garbage collection algorithm implementation. Any, right? As long as your garbage collection algorithm is basically, graph traversal and manipulation of these kind of heap-like data structures, you can apply this cost analysis framework to them, which is incredible, right? That's the main meat of what they're doing. It breaks down cargo-culted beliefs, right? It takes this idea that you choose one or the other, and it says, well, actually, right, what you do is you design your garbage collection algorithm around the workload that your application needs to perform, right? So you don't just choose one or the other. You are going to end up choosing a combination of the characteristics of those two, and either you can do so intelligently through the framework that they present, or you can start with one and then like beat it with a bat until it looks like the other one, and you're not going to be that happy with that result, right? And they say that nearly all, and it's really like, just because I knew someone in here was going to bust my chops if I said all, there are no production garbage collection algorithms that are one or the other. There just aren't. You're not going to, I don't know, unless you know of any. Like your toy implementation that you do in computer science class will be one or the other, right? For very simple virtual machine implementations, that's great. But when you're talking about optimizing, you will end up doing one or more of these things, specifically in the current state of like 2014 computer architecture. That's typically what will end up happening. And then they make real design recommendations. That's the other really cool thing about this paper, is that they say for people who are designing garbage collectors, you can be doing so more methodically. And to me, that was really powerful, because it was this paper came out of people that had implemented many garbage collectors, right? So after implementing reference counting garbage collectors and optimizing them, and implementing tracing collectors and optimizing them, they stared at that for so long that they started to see these similarities between these two things. And for me, that is the most powerful type of insight that you can have in the field of computer science, right? The best, for me, most visceral and awesome, mind-blowing computer science are these crazy abstract connections between things that seem so sort of, profane and like real world, right? Like they're in the flesh, right? But if you stare at them for long enough, you can start to see these deep connections. And they like to use that word, like deep connections, algorithmic duals, right? What does that even mean, right? Okay, and that's really powerful. This is the most important aspect of that. So they said that our firsthand experience of and frustration with the convergence of optimized forms of reference counting and tracing collectors led directly to a deeper study of the algorithms in the hope of finding fundamental similarities that seem to be appearing in practice. So they were like, okay, here's a hypothesis. They're similar. And then they proved that they are, right? This isn't someone's opinion, right? Okay, if you believe in, formal mathematics and proofs, I consider this truth. It is a fact that these algorithms are duals of each other, and that's not refutable unless another proof comes out that refutes that. Okay? Not refutable. Okay? So I like this quote. And then, so this is like the up really late smoking dope version where they're like, tracing operates on live objects or matter, while reference counting operates on dead objects or antimatter. For every operation performed by the tracing collector, there is a precisely corresponding anti-operation performed by the reference counting collector.
Whoa, dude.
That's a fact. Whoa, dude. Right? Okay, so all of that is gospel, right? Now we can relook at that table that I showed you that compares the naive implementations of reference counting and tracing, and here's the 21st century version. Tracing and reference counting have starting points, right? In tracing, you start from the roots, and in reference counting, you start from the anti-roots. In the graph traversal aspects are, what's that?
Can you say what an anti-root is?
Yeah, so I can. Yeah, so in reference counting, the idea is that you start with an overestimation of the number of references that exist to a given area in memory, and you decrement them until they get down to the true count. And then once you know that true count, you know whether or not you actually need that area of memory hanging around, right? So you are like starting with what you don't need and figuring out what you need from what you don't need. And that's why it's hard to explain, sort of. You kind of have to read it a few times, but the forward from the roots thing is like it's an implicit component of mark and sweep algorithms, right? That's always how they work. You walk through the heap and you're I'm using you, and then you know, right? So if you have, like I said, if you have 10 marbles, right, and the algorithm on the program that you're running is using 1, 2, and 3, right? You just mark 1, mark 2, and mark 3, and then during the sweep phase, right, you know that there's 10. So you go through 0 through 9, and you say, am I using you? Yes. Am I using you? Yes. I'm using you. Yes. Am I using you? No, I don't need this area. I can allocate from this area, right? So in tracing, you start from what is known to be being used, and in reference counting, you start from what's left of that, right? That's as good as I'm going to do right now. So in object traversal, in tracing, you trace what's live, and in reference counting, you trace what's dead. The initial reference count in tracing is low, and the initial reference count in reference counting is high. Oh shit, I got that part right, okay. And in reference counting and construction, you add to that low number until you get to the accurate number, and in reference count reconstruction on the reference counting side, you subtract from that overestimate until you get to the actual estimate, and then this last line, which we didn't really discuss, refers to those specific optimizations that tend to be applied, where in the extra iteration, the extra work that you need to do, because there's always extra work that needs to be done, in tracing algorithms, that's during that sweep phase where you actually do that deallocation, and in reference counting, they call something called trial deletion, which is basically a different formulation of that idea. I don't know. I kind of bailed on the slide a little bit. That's all right. Okay. So another awesome contribution of this paper is these awesome diagrams, okay? And these are the really simple ones, right? But okay, if you just look at these four, whatever they are, right? They're 4 things, okay? They look really similar to each other, right? Okay? They're really simple. On the left bars are the roots or the anti-roots in a given algorithm, right? And the C stands for counting, and T stands for tracing. So in pure tracing, you use tracing to count from the roots to the heap and also within the heap. And in pure reference counting, you use counting to keep track of what's going from the anti-roots to the heap and then also from within the heap, right? And then the next line is that first level of optimization, where the first thing you will do to optimize your tracing algorithm is to use counting to keep track of the what's being referred to from the roots to the heap, and then use tracing within the heap. And then the first optimization that you will tend to do to reference counting algorithms is to use tracing to keep track of what's being referred to from the anti-roots to the heap, and then use counting within that heap, right? So they did all of that work and all of that formal basis just to be able to sort of graphically depict that you just pull from the other side in order to optimize the particular algorithm that you started with. And they characterize some very complex algorithms using this system, and those of you who have read the paper or started reading the paper, if you just flip through, you'll see that even the most complicated, distributed garbage collection algorithms, whatever it is, can be expressed using these kinds of diagrams. Okay, so just a little bit more about why I love it, and then I'm going to finish up. So I love this paper because it emphasizes trade-offs, not garbage collection trade-offs, but it emphasizes trade-offs just in general. It says that in order to choose the right garbage collector, you need to think about the workload that your application, what it's doing, right? And they give some really interesting examples where they say that, they talk about, for example, some optimizations to reference counting that would typically be a terrible idea unless, right, you were working with, I think it's like a log structured file system, right? So if the allocation and deallocation that you're doing has to be written to disk, right, each time you do it, that would probably significantly change the picture of which algorithm you would choose, right? So I don't know if that makes much sense to everyone, but in other words, through this framework they can show that what matters is what kind of work your program is doing, not what is the fashionable algorithm to use or which one you have heard is the right one to use. The right one to use is the one that applies to your workload. And that's, I think, something not only in garbage collection, but in general, that's really easy to overlook as engineers. You just want to, I don't know what you want to do. You don't want to think about it. You want to do this or do that or use an algorithm, just borrow from someone and all that. It's great. But when it comes down to it, what you really need to do is consider the space-time trade-offs in whatever it is that you're implementing or choosing to use. It also specifies areas of focus for design. It goes through a bunch of properties where, in reality, you're not choosing between reference counting and tracing. You're choosing between whether or not you will partition your heap or you won't, and you're choosing between, do you need things to be fast or do you need them to take up a small amount of space? There are other things that you're actually considering when you're choosing which garbage collection algorithm will be appropriate for your workload. And finally, it's just a really neat and novel paper where two very different kinds of algorithms are shown to be very closely related to each other in a way that really just kind of blew my mind the first time that I really understood what these authors were communicating, where you can use math as the sort of intermediate representation of these code algorithms, and then once you have this formula that which you can use to express the trade-offs that are inherent in those choices, that you can make intelligent scientific decisions about that implementation. And that's something that is very hard to do. And like I said, I feel like that kind of insight is really as good as it gets in computer science. And that's not a derogatory thing to say. Okay, cool. So we can hopefully have a little bit of discussion now. I've been speaking for 44 minutes. So here's some thoughts, some potential discussion points. Maybe I'll just go drink more beer. That's fine with me too. So are there other algorithmic duals? Can anyone think of anything that works in that way?
Yeah, so I think that vocabulary comes from optimization. Because for every, they call it your optimization problem that you come up with is called the primal problem, and then there's a corresponding dual problem. So one of them, the primal problem is what do I buy to get the most value while spending my target? And the dual problem is what do I,
How much can I get for my money?
yeah, how do I fit things in? There's a very like rigorous way you can switch between the two formulations of the problem, and there's a relative bound where when you solve one, that tells you a bound on the other solution.
Okay, cool. Did everyone hear that? So it comes from optimization. It comes from optimization theory. Is that a way to talk about it? I tried to
Is there a
look.
paper for you to speak about? Is that what I'm hearing?
I tried to find. I'd love to see if you have any references for that, because they don't cite anything specific to that language.
If you just search for the word primal dual.
Primal dual.
Yeah.
Primal dual. Okay, so this is one of those scenarios where, like, my lack of academia is showing, and that's good. I'm comfortable with that. So
that's
great.
true of every graduate student ever.
Right,
You have to
yeah.
have some old dude who's like, no, here's
Here's where it
just
is. So
bestows.
I have an idea. I don't think this definitely doesn't fit your case, but one framework that I've sort of thought about in similar contexts, and if you read the blog post that I wrote about this, I think I mentioned at the end. One thing that I like to think about in a similar context is like the relationship between functional programming and object-oriented programming, right? Where they're not algorithmic duals of each other in any sense, right? But if you take one and you take the other, right? And there's a whole bunch of people that think they're inherently different, right? And then you read like the Art of the Meta-Object Protocol or something like that, or you read a more like Brian Merrick's Functional Programming for the Object-Oriented Programmer. You see that you can take a purely functional language and implement objects in it, right? Or you can, or what?
So we're talking about this more next time.
Yeah. Okay. So that's one thing. That's as far as I was like that made sense to me. Yeah.
So this isn't from computer science, but I can't help but think that this sounds a lot like Derridian deconstruction, where they take like two things that you think are completely opposite, and they indicate that they're on a continuum, and then are able to like theoretically draw that out.
Yeah, so there's like postmodern theory that has nothing to do with, which is my background. I have a philosophy degree. I studied philosophy, so maybe that's why I like this. Where making abstract frameworks out of things in Derrida's sense, right? Deconstruction is this idea. Deconstruction is this idea that you can just take. That's really good. I like that. That's great. Were you going to say something?
You wrecked my mind with Derrida.
Okay.
So there's
Good. Yeah.
in the world of real things, there is particles and waves,
Okay.
and frequency analysis versus time series analysis.
Okay. Could you elaborate on that at all, or
Well, is it a particle or is it a wave?
is it a particle or is it a wave?
Yes.
It's supposed to be one or the other,
Ah.
but it's both at the same time.
Okay, I like
Depending on where
that.
you observe it from.
That's good.
Right.
That's great.
And there are some problems that are solved more easily in the frequency domain versus the time domain. And when you're having trouble in the frequency domain, you can switch over to the time domain.
Yeah, I like it. I try to do that as often as I can. What?
Do you have a fixed point?
I have it. We can talk about it. Yeah. So we can talk about the details of the fixed point formulation. That's another thing that's like kind of intense, but we can talk about it. We can talk about these trade-offs, partition and traversal, and then we can also potentially discuss this automatically tuned GC's idea, where what they say toward the end of the paper is that they have like a sentence on it at the end. It's kind of awesome. Where they're like, oh, by the way, maybe this means that people can actually have automatically tuned garbage collection algorithms, and maybe the JVM doesn't have to have 7,000 knobs in order to achieve optimization. Maybe you could start from a certain point and hint it and tell it, hey, I might be doing this workload, or it can listen to how that workload changes over time. And I know those things kind of exist. No, they don't really exist, and especially not in mainstream application. Right? We're talking about special hardware instruction style garbage collection algorithms have some of those properties where they say maybe you could start with one and the garbage collector should just know what to do based on the workload that it's processing. Okay? So yeah. Any questions, or does anyone want to? We could talk about the fixed point formulation. Should I bring that up? Do you want
I just
to
think
talk
it's
about
the
it?
coolest part. But I'm a math geek a little bit too, so
A little bit.
yeah.
Yeah, I think it's really cool. I can show that. Does anyone else have any questions, or?
Well,
yeah.
yeah, maybe this relates to that.
Yeah.
You mentioned that they use some real mathematics to show this duality or whatever. Is that what you're referring to?
Yeah, that's part of it.
Part
Yeah,
of it?
yeah. Let's take a look at it.
Yeah.
Okay. Yeah, let's do that. So here it is. Yeah, this is proof that I read it right here. Purple. Oh, you can't see it. What the fuck? Okay, look, it's purple. I know what that means. Okay, cool. So let's see.
I like that its name is bacon garbage.
Bacon garbage, yeah.
Yeah,
that was
yeah,
good. People like
that's
that,
fine.
yeah, bacon
Yeah.
garbage. Okay, so basically what they do is, so let's take a look here. Let's take a look here. All right. This is cool. This is like, these are two pseudocode implementations, one of tracing and one of reference counting, and you can kind of see, similar to that table where they had the same number of rows, like they're lined up, they look a lot alike, right? Don't worry about what they say, just kind of just squint, you know? And it makes sense. The same applies to everything that I'm saying.
That's
Okay. So right here, this is cool stuff.